Good afternoon. Thank you, Thomas, for the introduction. So my name is Yann Thanwerdas. I'm a first-year PhD student at INRIA in Sophia Antipolis. My PhD advisor is Xavier Pennec. And I'm going to talk today about Spd matrices, so symmetric positive definite matrices. The main goal is to find some principles to give a sort of classification of the existing Riemannian matrix on the Spd manifold. And so I'm going to present to you two articles. The first one is affine invariance well defined on Spd matrices, a principled continuum of metrics, is the fourth one indicated on the schedule. And the second one, exploration of balanced metrics on symmetric positive definite matrices, is the second one. So beware with the order. So first, I would like to give some background about the Spd manifold. Then I will present this paper about affine invariant metric, or more generally, metrics that are invariant under the general linear group. The first part of the talk will be very similar to Min's first part also, because where he is focusing on the Procrust or the Burr-Wasserstein metric, we will focus on the affine invariant metric, and then I will present the other article about balanced metrics. It's a principle that will allow us to encompass more metrics that already exist. So first, let's talk about Spd matrices in general. So as Min said, Spd matrices are used in many applications as covariance matrices, as correlation matrices, as Toplitz matrices. We saw that in many talks. It can deal with brain-computer interfaces, fMRI, computer vision, radar, many applications. But here we focus more on the Riemannian viewpoint. So when you have symmetric matrices, we know that their eigenvalues are real, and Spd matrices are symmetric matrices with positive eigenvalues. So this is a convex cone, an open convex cone. And I'd like to give some tools that will be helpful, useful, I mean, in the following. So the exponential, the matrix exponential is a tool that we can define on any matrix. But the main point is that it's a diffeomorphism between the vector space of symmetric matrices and the convex cone of Spd matrices. And we can define its inverse that we denote log. And so we can define the power functions that are compositions of the exponential and the logarithm. And these are also diffeomorphisms of the Spd manifold. So in the literature we have many metrics, Riemannian metrics, and we would like to put some order in this zoo of Riemannian metrics. So the first principles we can think about are invariances. For example, many of them are invariant under the orthogonal group action. And another way of classifying them focuses on the curvature, the sign of the curvature. So the Burr-Wasserstein metric, the Procrust metric, is positively curved. Some are flat, some are negatively curved, and some are even have the sign of the curvature is unknown. So So first we're going to talk about these flat metrics. Actually, the flat metrics in the literature are kind of already unified by the power Euclidean metric. Obviously, the Euclidean metric appears as the power Euclidean with power 1, the inverse Euclidean with power -1, and so the square root and everything. And the log Euclidean, as Min already said, is the limit of the power Euclidean metrics when the power tends to 0. So we already have a kind of unified framework for flat metrics. And we would like to find this kind of framework for a fine invariant metric. And it's already done for Wasserstein metric, because we have this family of alpha procrust, or we could have called them power procrust also, that encompass the Wasserstein metric and the log Euclidean metric. And about negatively curved metrics, so the affine invariant metric has been introduced as follows. When we take a random vector and we apply to it an affine transformation, its covariance matrix is transformed as written here. So this defines a group action of the general linear group, and we can find all the metrics that are invariant under this group action. These are written just below, and this is a 2-parameter family of Riemannian metrics. Usually we say that it's a 1-parameter family because all metrics are give the same geometry to the space up to a scaling factor, a global scaling factor. And the feature metric of the multivariate centered Gaussian model can be viewed as a particular case of this family, with alpha equals 1/2 and beta equals 0. So we already have some relations. And more recently, the polar affine metric has been introduced and claimed to have the same properties of invariance, especially the symmetric structure. And so we wanted to understand why the affine invariant metric and the polar affine metric have the same kind of properties. So it's defined as follows. The polar decomposition gives a diffeomorphism between the quotient space here and the Spd manifold. And so we can define the Frobenius inner product here, which is orthogonal, which is invariant under the orthogonal group. So we can define a unique Riemannian metric on the quotient that corresponds to the Frobenius metric, and then a unique metric on the Spd manifold thanks to this diffeomorphism that we call the polar affine metric. So what are the relations between the affine invariant and the polar affine metric? Does there exist a 1-parameter family of polar affine metrics as they exist for the affine invariant framework? So in the following, we will answer these questions in section 2 by unifying all these, the affine invariant and the polar affine metric, and we are giving some relations between the other metrics. And then the section 3 will be about balanced metrics. We observed that the affine invariant metric and the BKM metric can be expressed from other metrics, and we are trying to generalize this principle to define the mixed power Euclidean matrix, I will show you. So before that, let's go to the Riemannian matrix invariant under the general linear group. So with the Cauchy space formalism, so the one that thanks to with the polar affine metric has been introduced, we can I said that we can push forward the Frobenius inner product, but the main property is that it's invariant under the orthogonal group. So we can find all the inner products on symmetric matrices that are invariant under the orthogonal group and push them to the Spd manifold. And by doing that, with this diffeomorphism, we find a one parameter family of polar affine metrics, and with this diffeomorphism, we find the one parameter family of affine invariant metric that was already known. And the only difference between the two is this square function. So in other words, the polar affine metric is a square deformation of the affine invariant metric. They are isometric. With the group action formalism, we can also define a group action on the Spd manifold that differs from the affine action, but this is also fine, and this is a group action, and this gives rise to the one parameter family of polar affine metrics. So once this done, we can replace the power 2 by any power and define the power affine matrix, and we can even replace the power functions by any diffeomorphism of the Spd manifold and define the deformed affine metric. So it's a very general framework. And these metrics are all invariant under a certain general linear group action, but the action differs with the function. And to relate with the Main's work, when the power tends to 0, we can recover the log Euclidean metric. So the log Euclidean metric appears as a limit case of the power Euclidean matrix, the power affine matrix, and the alpha Procrust matrix. And to give the relation between these metrics, these deformed affine metrics, and the Fisher matrix, the only thing to change in the Gaussian model is to replace the parameter sigma by a parameter f of sigma. So it's still Gaussian, but we have changed the parameter, and when we derived the Fisher metric, we find exactly the f deformed affine metric. So this was for GLN invariant metric, and now let's go a bit deeper with this principle of balanced metric. So we know from Amari that the Fisher metric, even before Amari, that the Fisher metric of the centered Gaussian model is the affine invariant metric. The mixture and exponential connections are the Euclidean Levi-Civita connection and the inverse Euclidean Levi-Civita connection. And so there is a relation between the inverse Euclidean metric, the Euclidean metric, and the affine invariant metric. And we can observe it thanks to the formula. When we see this formula, there is one part that comes from the inverse Euclidean metric and one part that comes from the Euclidean metric. Similarly, the BKM metric has been introduced with a different expression, but it can be proved that it's equal to this expression. And it appears that it's also a kind of hybridization between two metrics, the log Euclidean metric here and the Euclidean metric here. So we wanted to find a more general principle to encompass these two. And we proposed the principle of balanced metrics. So we can take two flat metrics, G and G star, denote their Levi-Civita connections by nabla star, and their parallel transports by pi and pi star. And we can define balanced bilinear form, G0, by the formula just here. So taking into account the trace and the parallel transports of the two original metrics. And the theorem is that if this bilinear form is a metric, then we get a dually flat manifold because of this relation, because it's the dual parallel transport that preserves the metric. And so we can define the mixed power Euclidean metrics, at least the mixed power Euclidean bilinear form at first, which is written here. We take two different powers and we hybridize them into the trace. And this bilinear form happens to be symmetric and positive definite, so it's a metric. And hence, thanks to the previous theorem, this manifold is dually flat. So thanks to this formalization, we now have a family of a two-parameter family of mixed power Euclidean metrics then that contains many of the metrics that were introduced first. Here we have the Euclidean, the log Euclidean and inverse Euclidean, because the powers are equal. So this represents the line of the power Euclidean metrics. Here the power are opposite, so we get the power affine metrics, and here obviously the affine invariant metric, which is inverse consistent, so it's here too. And now we can also get from the log Euclidean and the Euclidean metric the BKM metric. So this family of mixed power Euclidean metrics contains many of the Riemannian metrics that are in the literature. And that was my conclusion. Thank you for your attention.